Okay, so this is really similar to the last thing that we left off with. So all we're doing here is we're multiplying and factoring polynomial expressions. So we're using a table as an aid. So if I take a look at this table, I've got x times x, which they already did, x times 3, so I'll go ahead and write all this out. So x plus 7 times x plus 3. X times x is x squared. And then x times 3 is 3x. And then 7 times x is 7x. And then 7 times 3 is 21. And then I can combine like terms. 3x plus 7x is 10x. And then 21 goes over here. And we're done. And that's exactly what this is saying. So x squared, 7x plus 3x, that's the same as what I got over here, and then 21. And then if I add along these diagonals, I'll get the same thing. So x squared plus 10x plus 21. And then they're saying use a table to aid in finding the product of 2x plus 1 times x plus 4. Well, we can do that. So 2x plus 1 up there, x plus 4 here, and then let's just multiply these out. So 2x times x is 2x squared, 2x times 1 is 2x, 2x times 4 is 8x, and then 4 times 1 is 4. And then I'll just add across these diagonals, and I've got 2x squared, 2x plus 8x is 10x plus 4, and that's it. We're done with that piece. So polynomial expression. A polynomial expression is either a numerical expression or variable symbol, or the result of placing two previously generated polynomial expressions into the blanks of the addition operator or the multiplication operator. So if you take a polynomial expression like 3x plus 5 plus 3x squared plus 6x plus 5, that is a polynomial expression. And then if I take these same things and I multiply them, or if I take 2x plus 2 and multiply it by x plus 5, whatever, doesn't matter. These are just examples, x plus 5 there. Then that is a polynomial expression. So these two are two polynomial expressions. They're called binomials. If you multiply them together, they make a trinomial, but polynomial times polynomial equals polynomial. Polynomial plus polynomial equals polynomial. So down here, multiply the following binomials. Note that every binomial given in the problems is a polynomial in one variable x with a degree of 1. Write the answer in standard form, which in this case is ax squared plus bx plus c. So this is telling you to write the square term, or the highest power, first. So polynomials in standard form tend to decrease in power. So x times x squared. X times negative 7, that's going to be negative 7x. Let me write that. X times 1, 1x. And then 1 times negative 7, negative 7. So then x squared, negative 7x plus 1x is negative 6x minus 7. So that's it. So then if I go down here and I multiply these, x times x is x squared, and then I've got 2x. 9 times x is 9x. 9 times 2 is 18. So I'm left with x squared plus 11x plus 18. Not 118. 18. So similarly here, x times x is x squared, x times negative 3, so x squared, negative 3x, negative 5x, negative 3 times negative, or negative 5 times negative 3 is positive 15. Negative times a negative is a positive. So I'm left with x squared minus 8x plus 15. All right, now for the hard ones. So just remember your rules of fractions and you should be fine. We're going to do this together. So x times x is x squared. X times negative 1 is going to be negative x. So that's the second one. 15 over 2x. So 15 over 2 times x is just 15 over 2x, and then 15 over 2 times negative 1, which is going to be negative 15 over 2. So if you take a look here, I can convert this fraction. I've got negative 2 divided by 2. So all I'm doing is taking this negative 1 and converting it. If you take a look here, negative 2 divided by 2, if you type that into your calculator, that's the same thing as negative 1. And the only reason why I did that, I changed that coefficient, is so I can add these two x's. Okay? So if you take a look now, negative 2 over 2 plus 15 over 2, that's going to equal 13 over 2x. So I can add fractions as long as the denominator matches. That's the reason I didn't add them here, right? So negative 1 is the same thing as negative 2 over 2. 15 over 2 commutes with negative 2 over 2. I can easily take 2 from 15 and get 13 over 2x. So I'm not finished, so there we go. So that I just wanted to explain that fraction in case it's confusing. And we're going to do something similar here, okay? So x times x squared. X times negative 3 fourths, so negative 3 fourths x. And what's nice about this is whenever we distribute this negative 5 fourths, we can actually combine like terms easily because you don't have a different power. And then last step, just remember your rules of multiplication. You can look this up. Whenever I multiply two fractions, you multiply the tops, the numerators, and the denominators. So you multiply numerator by numerator and denominator by denominator. The only time you cross multiply with fractions is if there's an equal sign between. So don't forget that. If you're multiplying two fractions, you need to multiply across. If you have an equation with fractions on both sides of the equation, you're solving for a variable, then you can cross multiply. So negative 5 times negative 3 is positive 15. So the negative only modifies the top of the fraction. That's important to note. So this is negative 3 divided by positive 4. And this, negative 5 divided by positive 4. And this is negative 3 divided by positive 4. So negative 5 times negative 3 is positive 15. 4 times 4 is 16. And that's it. So then I just combine like terms. So negative 3 minus 5 is negative 8 over 4. X plus 15 over 6, but 16, not 15 over 6, 15 over 16. Negative 8 divided by 4 is negative 2. So I can simplify that more. So describe any patterns I worked. So now it's saying to factor the following quadratic expressions. Well, there's some steps to factoring. I gotta stop. Okay, so let's talk about how to factor. So to factor, right, we're gonna follow some steps. So, and I call this one up here step 0. So we'll talk about that. So step 0 is to find a GCF first, or rather, not find, but look for. That's what I want to say. Look for a GCF first. So look for a highest value that each one of these things is divisible by. So if you take a look here, my a term is 1. Anytime you see x squared by itself, there's nothing here, it's understood to be 1. But in this case, there's nothing there other than 1. So that means the highest number that I can divide all these terms by is 1. And then the highest variable I can take out is nothing. There's no x with the 7. So not, what I'm trying to say is that each term does not have an x in it. So there is no GCF in this one. There may come up in some other problems where I have a GCF, but this one does not have one. So after we look for a GCF, the next thing we're going to do is find two numbers that multiply to be a times c, but add to be b. Okay, so if you take a look over here, I've got a times c, which is 1 times 7. So a times c is 7. So a equals 1, b equals 8, and then c equals 7. So if I take a look at these terms, a times c is 7. Now, let me just say, whenever you're looking at the a, the b, and the c, I'm talking about a quadratic of the form ax squared plus bx plus c, okay? And the a, the b, and the c are just the coefficients and the constant term. So a is 1, b is 8, and c is 7. b is not 8x. It is just 8. c is 7. A is just 1, not 1x squared. So the variables will never carry in this step. So a times c in this case is 7. So we're trying to find factors of 7, which is easy because 7 is prime. We talked about that. So 1 and 7 multiply to be 7, but add to be 8. So whenever you're looking at these factors, you're looking at their sum as well. So the sum is not 7, but 8. So those are my pairs. So what I'm going to do with those is I'm going to split up the x term. So over here, step 2, split up the x term. So I've got x squared and then 7. So those two values are not the x term or the variable term. Split up the x term or variable term. Going off the page there. If I split up 8x, I can split them into those two factors I found. So 1x and 7x. And then my next step is to group first two terms and last two terms. So if I group the first two terms, that's just saying x squared plus x. So I just got rid of the 1. That's not really, anytime you see an x, it just means 1x. And then 7x plus 7. Now, I'm going to say this, and I want to make sure that you guys understand it. Whenever you group these terms, there's a plus sign between. That's important. If you don't write this plus sign, you're saying that you're multiplying these two parentheses. So that plus sign is pretty important, okay? So the fourth step is to find the GCF. In both parentheses, and then factor. Okay? So right here, x squared plus x, they both have an x term, so I can factor that x out. I can undistribute that x. So I'm left with x plus, not 3. Sorry, I did that one earlier. I'm left with x plus 1. And then both of these terms are divisible by 7, so I can write 7x plus 1. So now x plus 1 and x plus 1 match, so I can factor x plus 1 out of the expression. So I'm left with x plus 1, and then here I'm left with x plus 7. And so the whole goal of this, whenever you're dealing with these factorizations, is there is a standard, and I'll show it to you. Hold on, let me just search it real quick. Okay, here we go. So oop, almost had it. Keyboard, here it is. Control F. Not gonna work. there a find on page? Yeah, there it is. Okay, so find on page, Control F, Algebra 1. And I need not the 1, but the I, because for some reason we're using Roman numerals. Okay, so here's your standard. Your whole goal for this is to, and I'll write this, identify zeros of polynomials when suitable factorizations are available. Okay, so we just did that. We just factored the polynomial. The only thing we have left to do is identify a zeros. So there's a suitable factorization available to us, and we just factored that quadratic. A quadratic is a type of polynomial. And we use the zeros to construct a rough graph of the function. We haven't done that yet. We have to identify the zeros and then draw a rough graph of the function. But that's pretty easy, okay? So what we just did was find x plus 1 and x plus 7. So to find where this function, where this quadratic hits the x-axis, I'm just going to set it equal to 0. And then I have to set each factor equal to 0. So I'm going to go over here, x plus 1 equals 0, and x plus 7 equals 0. So x equals -1, and then x equals -7. And I'm taking a look at this, and I'm saying that these are my zeros. You'll call them roots, or x-intercepts. Anytime you see any one of these with a quadratic, if it asks for the zeros or the roots or the x-intercepts, that's your cue to factor, okay? So we just factored, but some questions will ask you to find the zeros, the roots, or the x-intercepts. The reason why we do that is because we can see where the function hits the x-axis. So this particular function hits at, I'm going to just draw a rough graph here, -7 and -1. So it looks something like this. Now you might be wondering like how I know which way the quadratic looks, like what the quadratic looks like and why it's bending that direction. So quadratics, I'm just going to make a nice little aside here. For quadratics, they come in two flavors, okay? They're either pointing up like this or they're pointing down like this, okay? Whenever you're in the form ax squared plus bx plus c, whenever you're looking at a standard form of a quadratic, you can tell whether they bend up or concave up if a is positive. And then you can tell whether or not they're concave down when a is negative, okay? So they will bend down or they will be concave down like this if a is negative. They will be concave up if a is positive, so like a U version of the quadratic. And then if you take a look over here, my a term was 1, and that's why I drew it as concave up. Now, again, the roots are accurate, the shape is accurate, but it's a rough graph of the function. Oops. Oops. It's a rough graph of the function, so it's not perfect. But if you type it into a calculator, graphing calculator, that quadratic will bend up and it will hit these two values. So let's do a few more. I'm going to do m squared plus m minus 90. And I think I'm going to do it on here. So maybe this will be a little more easier to see. M squared plus m minus 90. So, right, our first step is to look for, or step 0, if you will, is to look for a GCF. So look for a GCF. Step 1 is to find two numbers that multiply to be a times c, but add to be b. Okay, so we did this a few minutes ago, but you can have quadratics that have different variables. So in this case, I've got m squared and m. It's the same thing as writing x squared and x. They're just different inputs. So the variable might mean something different. It might represent, I don't know, muffins, and where the other ones represent xylophones. I don't know, I don't care. But the variable is just a placeholder for an input, okay? So in this case, it will factor the same. I just have to go through the same steps and keep the m consistent. So whatever is up here, I better have m's at the end and not x's, okay? So a times c, I would need to find my a, which is 1, right? My b, which is also 1, and my c, which is negative 90. So I'm looking for factors of a times c. So 1 times negative 90 is negative 90. So I'm looking for factors of negative 90. So I can think and kind of look through here, and I can kind of think about factors of negative 90, and some of those factors would be, well, I could do negative 3 and negative 30. That would, or positive 30. That would work. And since this value is negative, I can do negative positive and then positive negative. So if I do this, I get positive 27 here for their sum. So remember, we're adding across these rows, right? Negative 3 plus 30 is 27, which is not our b term, so this pair won't work. And then similarly, right here, I've got negative 27. I'm trying to make this as neat as I can. Okay, so let's look for some other factors. Okay, so negative 3 and 30 didn't work. Let's try negative 1 and 90, and then their counterpart. Well, that's going to be just 89 and negative 89. So sometimes you just have to play with these values. Okay. And then down here, I can do, I don't know, 10. Yeah. So 10 and 9. So 10, negative 9, or negative 10 and positive 9. And there are more factors than just that. You could do 5 and, I don't know, some other number. I think 5 and 18, yeah. But positive 10 minus 9 is positive 1. Negative 10 plus 9 is negative 1. So we've actually found our b term. So our b term was 1, and this sum is 1. So that means that the factors that we're going to split the variable term into are 10 and negative 9. So I'm going to come over here and split my variable term. And then out of these two, I can factor an m out. So m squared divided by m is m, 10m divided by m is 10. So I've got m plus 10 left. Both of these terms are divisible by negative 9, so I can factor out negative 9, and I'm left with m plus 10. So right here, this parentheses and this parentheses match, and that means I can factor them out as a GCF. So I'm left with m plus 10 and then m minus 9. And so in this case, right, the two zeros of my quadratic would be 9, right? Because if I plug 9 in this, I'm going to get 0. And if I plug negative 10 into this, I'm going to get 0. So, or I can just set the entire thing equal to 0, and I can solve these two equations. So I'm going to explain it that way. So m plus 10 is set equal to 0, and m minus 9 is equal to 0. So if I subtract 10 from both sides of this equation, I get m equals negative 10. And then if I add 9 to both sides of this equation, I get m is equal to positive 9. And if that's the case, positive 9 somewhere over here, negative 10 is like right there, something like that. And then my quadratic, my a term was positive, so my quadratic should be concave up, so something like, I don't know, this. So if you graph that in a graphing calculator, you'd see something like that. Okay, so that's what my quadratic looks like. So just to recap, right, our standard is talking about, yeah, our standard was mentioning something about identifying zeros of polynomials when suitable factorizations are available. That's factoring. So if we can factor a quadratic, we're good with that. Graphing is limited to linear and quadratic polynomials. So linear as well. So you can need to be able to find x-intercepts of lines, but we've done that before in this class. And then we use those zeros to construct a rough graph of the function defined by the polynomial. If we have our a value and we have our zeros, we can construct a rough graph. If a rough graph is what I'm figuring in this situation is that they use the zeros in the general shape. If that's not it, I don't understand exactly what they're looking for with that standard, but I am pretty sure that is what they mean. Can you construct a rough graph if you're given the values? So that's all well and good. So let's take a look. Might just do one more example. Okay, so I'm looking at factors of a times c. So I won't write the steps because they're already written. So a, b, and negative a, b, and c. And then I'm trying to find factors of 40. So my factors of 40, my little chart, are going to be, well, 2 and 20 work. And they're both going to have to be negative in this case. So let's see some other ones. -4 and -10. I don't know, -8 and -5. Let's see, -1 and -40. And then what else could work? Trying to think what else could work. But you know, you could spin your wheels and you could use your calculator and divide it, and there probably is another factor. But if you take a look here, I've already got my pair. -8 minus 5 is -13. So they multiply to be negative or positive 40, and they add to be -13. So that's my pair. So I'm going to split up -13k into -8k and -5k. So out of the first two terms, I can factor a k out. So I'm left with k times k minus 8. And then over here, you can factor a -5 out. And the reason why we're going to go with a -5 instead of a +5 is because these parentheses that result have to match. So if I divide -5 by -5, it's going to give me a positive k. -5 comes out to the front. 40 divided by -5 is -8. If we did a +5 out and factored that out, this would be a -k and this would be a +8. And that would not work out. So k minus 8 matches, and now I can pull him out to the front. And remember, whenever you're pulling something out to the front, whatever's left is this stuff. So k minus 5 goes in the next parentheses. So come back over here. So, yeah. K minus 5 and k minus 8 equals 0. So I'm saying that on this axis, right over here at +8 and +5, right? Whatever value I plug in here, I'm trying to find this equal to 0. Or k minus 5 equals 0, which is k equals 5, and then k minus 8 equals 0, which is k equals 8. I'm trying to find where that hits the x-axis. So it's going to hit there and there, positive a term, so the quadratic bends up. And then we get this fun one. And if you think about it, this is actually cueing us, right? One factor is negative, one factor is positive. My a term is 1. So if I factor negative 100, start this one out, right? I can do, okay, 100 and negative 1. And that's it. That's the factors. So if I can split 99v into 100v and negative v, I can factor this guy. V factors out of these two, so I'm left with v plus 100. And then over here, negative 1 factors out of these two, so I'm left with v plus 100. So this tells me that v plus 100 is a common factor, and then v minus 1 is another common factor. So this quadratic is weird for its roots. 1 is right here, and then like negative 100 over here, way over here, way over there, yeah, something like that, and then swoop, really big, real big guy. Okay, v plus 100, I'm showing you those roots, equals 0. So I got v equals negative 100 from setting this part equal to 0, and then v minus 1, I set that equal to 0, and I got v equals 1. And that's where those things are coming from. So quadratic expressions. If the leading coefficient for a quadratic expression is not 1, the first step in factoring should be to see all the terms in the expanded form have a common factor. So that's my step 0. Then after factoring out the greatest common factor, it may be possible to factor again. So in this case, 2x cubed minus 50x. So you haven't seen x cubed yet, but remember we talked about something similar to this. I have 2 and 3 x's, and then negative 50 and x. So right, if I factor this further, I know that 50 is divisible by 2. Right, it's 2 times 25. And I've got x over here. So 2 matches, x matches, and then I can factor 2 out to the front and x out to the front. So I've got 2x times x squared minus 25. And that's exactly what they did here. And then you can see x squared minus 25 is a difference of squares. So that's x minus 5 times x minus 5. So they're telling you to factor this guy out. So this is actually a nice little quadratic. Take a look. I've got negative 16t squared plus 32t plus 48. My a term is no longer 1. It's negative. So that means I know my quadratic is concave down. And the reason why it's concave down is because a is less than 0. Namely, my a term is negative 16, so that's less than 0. So the GCF out of all these terms, the thing I can divide out of all these terms is negative 16. So I'm going to do that. So negative 16 divided by itself is 1. So I'm left with 1t squared. 32 divided by negative 16 is negative 2t. And then 48 divided by negative 16, well, I think that's negative 3. Yeah. Yeah, 16 times 3 is 48. So now all I have to do is factor this guy. And whenever you find the GCF, you're factoring the inside expression. So t squared minus 2t minus 3 is my quadratic to factor. So a equals 1, b equals negative 2, and then c equals negative 3. Now this a is different from this a because it's talking about, okay, sorry about that. So right here, right, a equals 1, b equals negative 2, and c equals negative 3. Well, that means that I can go over here and I can say a times c is negative 3. So that means I'm looking for numbers that multiply to be, or factors of negative 3, numbers that multiply to be negative 3, but add to be negative 2. So if I take a look at this, 3 is prime, so I know 1 and 3 work, and I just have to decide where the negative goes. So negative 1 plus 3 is positive 2, and then 1 minus 3 is negative 2. So 1 and negative 3 are my terms. So I'm going to split my variable term, negative 2t, into positive 1t and negative 3t. So down here, let me just zoom in some. So negative 16, got t squared, minus 2t, oh no, should be minus 3t. Yeah, minus 3t. minus 3t plus t minus 3. And then over here I can factor a t out of these, so I've got t times t minus 3 plus parentheses t minus 3 in parentheses negative 16 on the outside. So t minus 3 matches here. So I've got negative 16 parentheses t minus 3. And then what's left is this t and this 1. Remember, even with parentheses, if there's no number there, if there's a plus sign between, it's understood to be 1. So I'm left with this t and this 1, so t plus 1. So this tells me that my zeros, right? I can find my zeros, so t minus 3 equals 0. So that means t equals 3 if I add 3 to both sides of that equation. And then I've got t plus 1 over here. I set that equal to 0. I can subtract 1 from both sides. I get t equals negative 1. So that tells me that my quadratic equation will hit the x-axis, or the t-axis in this case, at positive 3 and negative 1. But remember what we said? We said earlier that this is a negative 16. So because that negative 16 was at the beginning of our quadratic, that's telling me that this quadratic is going to be concave down, okay? Even if it's factored out of the expression and the resulting polynomial on the inside, this quadratic on the inside of the parentheses, if the a term is positive here, that has nothing to do with the a term we factored out, the term we factored out. So if this was negative, that means that negative has a distributive quality to it. So this distribution of negative 16 would flip that a term to negative 16. So it's still concave down. So there's our rough graph. And here's our lesson summary. So multiplying binomials is an application of the distributive property. Each term in the first binomial is distributed over the terms of the second binomial. Area model can be modified into a tabular form model, the multiplication of binomials or other polynomials. So I can use those to multiply binomials or other polynomials when factoring trinomial expressions. Look carefully for a GCF as your first step. Do not forget to look for these special cases. The square of a binomial, the product of the sum and difference of two expressions. So here's some factoring ideas down here, some situations where you have to factor. So there we go. So I'm going to leave you, I think 1 would be good. Yeah, 1 and then 2.